Welcome to another podcast. In this episode, we're going to be taking a look at the formal definition of the derivative in terms of the limit and show how that's going to greatly simplify our task of finding the equation of a tangent line. So I'm going to start with just by writing the definition down. And quite simply, the definition is the derivative of the function f, that's the notation we use, at the point A is equal to the limit as h goes to 0 of f evaluated at a plus h minus f of a all over h. And if you were paying attention to the last video, then you know that this is the tangent, the slope of the tangent at the point x equal to a. So the derivative, which is this side, the derivative at x equal to a is equivalent to the slope of the tangent line at x equal to a, which is equivalent to this other limit as x goes to 0, or excuse me, as x goes to a of f of x minus f of a over x minus a. And we've thought of this quantity as being the limit of the slopes of the secant lines, but we've also thought of it as being the instantaneous velocity at x equal to a. So the derivative wears a lot of hats. It means a lot of different things. Geometrically, it's the slope of the tangent line at x equal to a, but it's also the instantaneous velocity of a particle moving with position function f at the point x equal to a. So being able to calculate the derivative effectively is an incredibly important part of this course and is a direct application of limits. Now, this is the derivative at a specific point. If I think of the derivative as a function, the derivative as a function is simply the limit as h goes to 0 of f of x plus h, with no a plugged in, minus f of x all over h. And so this is the formal definition of the derivative function. So the derivative function is given by this particular limit. Now, one other thing I want to add to this is if we think about our tangent line uses the point slope form, so it's y minus y1 equals m times x minus x1. And if we really think about this, we can replace a lot of these values with function values. For example, the point y1 is the function evaluated at a. The slope m is now given in terms of the derivative at the point a. So once again, this is the tangent line at x equal to a. X minus the original x value is a. So I can write the equation of the tangent line down immediately. The equation of a tangent line at the point A is simply given by this linear equation. So this is another thing that you should memorize definitely and understand from this video, and that is that this is the equation of a tangent line. At x equal to a. Now, let's actually apply that to a problem. So let's work an example here involving the derivative. And I'm going to start with, let's say the function is f of x equals 1 over x squared. And I want us to find f prime of x. And I also want us to find the tangent line. So find f prime of x and tangent line at, let's say, x equal to 3. So those are the two things I want to do. Well, let's start by finding the derivative. The derivative as a function is the derivative with respect to x of the limit as h goes to 0 of f of x plus h. It's f of x over h. Okay, so let's start filling this in. f of x plus h is x replaced with x plus h. So the function is 1 over x squared, so it's 1 over x plus h squared, minus f of x is 1 over x squared. All of that divided by h. Now, we've got a fraction inside a fraction, so that might bother you a little bit. But my suggestion is to go ahead and get a common denominator. First off, we're going to bring h into the bottom of each of these two. So this will be the limit as h goes to 0 of, a lot of times I'll just factor it out. So let's do 1 over h times, we've got the two fractions in the problem here. So this is probably the best way for most students to deal with it. Now we're going to get a common denominator for the fractions inside the parentheses. And that's easiest by cross multiplying and then multiplying the denominators together. All right, if we do that, then we can FOIL out the numerator into x squared minus, this ends up being x squared plus 2hx plus h squared. And we'll just leave the denominator alone for now. And this then is, you can see here in the numerator, x squared minus x squared. That cancels, leaving in the numerator a, don't forget the negative sign here, it's a negative 2hx, and then it's a negative h squared over x squared, x plus h squared. Notice how I'm not combining the denominator until I have to. I'm just going to leave it alone for now. So looking at that, what we notice is each of the terms in the top contains an h. So if I take the terms in the top and factor out an h, then they become negative 2x minus h over x squared, x plus h squared. And what I want you to realize is how far we've come here. If we tried to evaluate this limit directly, the problem all along was this pesky h in the bottom that was going to give us a 0 in the denominator. We've pulled that 1 over h out and managed to get a factor of h to appear on the top, so that now the thing we can do is cancel the h's. And by canceling the h's, we should try to reevaluate the limit now to see if things are better. So I'm going to take h equal to 0 and plug them in everywhere I see an h that's left, which would be those two spots. And the result of this is you get negative 2x minus 0 divided by, in the bottom you get x squared times x plus h is x plus 0 squared, so you get x squared times x squared, which is x to the 4th. And when you simplify, that gives you negative 2 over x cubed, which is in fact the derivative. So what we found is the derivative of this function is negative 2 over x cubed. Now later in the semester we're gonna explain why that's more significant than it already is, but it's incredibly significant to know that that is the derivative of the function f. But what it allows us to do for this particular problem is it allows us to now say, okay, if I wanted to know what is the tangent line at x equals 3, then my tangent line is y equals f prime at 3 over x minus 3 plus the function value at 3, just going based off the equation of the tangent line. So we just found the derivative. So if I take and evaluate that derivative at 3, it's negative 2 over 3 cubed times x minus 3 plus the function value at 3, so returning back to 1 over x squared is 1 over 3 squared. And simplifying, we get negative 2/27 x minus 3 plus 1/9. And we're done. But here's the lovely thing about this. I could ask you any value of x. I don't have to ask you just what's going on at x equal to 3. If I wanted to know what's happening at x equal to negative 2, I could just as easily do that simply by plugging in x equal to negative 2 into the derivative to find my new slope. And that's the real brilliance of knowing the derivative, is now I have the ability to find the equation of the tangent line at every single point of the curve 1 over x squared without having to go back through the limit over and over and over again. I do the limit once, and that gets me the tangent line everywhere by giving me the slope everywhere via the derivative. So we're going to do a lot more of this in class, but I just wanted to introduce the concept to you now. And we're going to have easier ways to calculate the derivative in the future, but for right now we're going to do it in terms of the limit. And this is the basic process described. All right, thank you for watching.